So conditional probability is maybe a term that you remember from last year, but we're going to explain it pretty simply with a very basic example. So in this example, I've got two different things that are happening in sequence. So we've got number one here, and the first thing that's happening here is that I'm telling you that I've rolled a die, which means that obviously we can have 6 possible outcomes for 6 numbers on the die. So if I asked you what's the probability of rolling a 2, you would most likely tell me 1/6, and you'd be correct because there's 1/6 probability for rolling any number on a fair die. Now, in the second part, I've now told you that the number I rolled was even. So what happens to my probability now? Well, technically, if we knew no information about the number that I rolled, then the probability would remain the same. But now I've told you some information, which changes the probability. And the way that we write that is the probability of rolling a 2, and then this vertical line, even. What this means colloquially is that I'm trying to evaluate the probability of rolling a 2 given I know that the number is even. So in this case, if I know the number is even, then obviously my only possible outcomes are 2, 4, and 6. So the probability of rolling a 2 would just be 1/3. And we know that makes sense because 2, 4, and 6 are the only even numbers that are valid, and there's only one that's 2, obviously, the one that we're looking for, and this is obviously 1 out of 3, and all of our outcomes are equal probable. So how did the probability change from here to here? Well, essentially it's because I told you a piece of information that kind of narrows down the problem. Now this is what conditional probability does. When you know a piece of information, it changes the probability of whatever we're trying to find. Now, the formula for this is A given B. Well, that's what we're trying to calculate. The probability of A given that B happens is equal to the intersection of those two things happening divided by the thing that's given to happen. So we calculated this based on common sense and knowing what the possible outcomes are. But if you have a more complex problem, then it's best to use this formula. Again, it's the intersection of both events happening divided by the piece of information that's given, the probability of that. Let's go to a basic example. In this situation, we have a standard 52 deck of cards. Assume that when we draw a card, we do not replace it. So that's just for any time where you draw multiple cards in this question, but I don't think that is applied here. Part A, what is the probability of drawing a 6? So if we have 52 cards, we know that 4 of them will be 6s. So the probability of drawing a 6 is equal to 4 divided by 52. And if we simplify that down, that's 1/13. Now, what is the probability of drawing a number less than 7? Okay, we'll think about what numbers there can be. And for this situation, we'll just assume that an ace is a 1, just for simplicity. So the numbers less than 7, we've got 1, 2, 3, 4, 5, 6. And the total numbers, or I guess we can think about the numbers that aren't included. We're just right at the bottom. 7, 8, 9, 10, Jack, Queen, King. Now, we don't really have to know them. It's just more to count them up and see how many possibilities we do have. So the probability of rolling a number less than 6, we can see that there's 6 possibilities out of 13 because there's 7 at the bottom. So we can write 6 out of 13. Obviously, we do have a 52 card deck, but you can see that, if it's randomly mixed up, then it doesn't really matter. If we did it the long way of calculating for a full deck, we would just get 24 over 52, which would cancel out to 6 over 13 anyway. Now, part C, what is the probability of drawing a 6 given that the card drawn was less than 7? So now this is a situation where I'm given that extra piece of information which narrows down my problem. Now, we can think about what will happen to the probabilities with the information given, and it should be a bit clear to you that if the card drawn was less than 7, then we've actually got a reduced sample space. And what does that essentially mean? Well, we've got less possibilities to choose from, which will in turn increase our probability. Now, this doesn't necessarily help our calculation, but it's more of a double check that I like to do whenever doing these types of problems. I think about, does the probability actually make sense in the context? And if it does, then you're probably right. And if it doesn't make much sense, then you might have done something wrong, and it's probably worth it just to double check you're working out. So if I wanted to calculate this, the probability of drawing a 6, given that the number was less than 7. So I can apply the formula, probability of 6 intersection less than 7 divided by the probability of rolling a number or drawing a number less than 7. And I've just realized I wrote this one wrong before. It should be less than 7. Now, the probability of 6 intersected with less than 7, we can think about what outcomes are common between both. Again, it's the intersection, so it's whatever's common between both. And that would obviously just be the probability of rolling a number 6, because less than 7 includes 6, but 6 only has its one instance. So it makes sense that 6 would just be the simplified version of the numerator. Now, the probability less than 7, I could just keep it like that. Now that we have both of these things to evaluate, we've actually calculated these in the previous parts. So the probability of rolling a 6 is 1 over 13. The probability of rolling a number less than 7 is 6 over 13. Now, with these types of questions, it's really useful to use that rule that we've probably been taught from primary school or even early high school. It's the state change flip when dividing fractions. So 1 over 13 times by 13 over 6. And this will really help cancel out things. We can see that 13 cancels out straight away. And now we have a probability of 1/6. Now let's just think again. Does this make sense in the context? Well, it should, because if we have numbers less than 6, we can see that less than 7, sorry. We've only got these 6 possibilities and we're just choosing the one from that. So 1/6 definitely does make sense. We didn't even need the formula. And it makes sense that the probability is increased from when we had no reduced sample space. When we're just drawing a number and we didn't know any information about it, it's just 1 over 13, which is comparatively lower than 1 over 6. So yes, it does make sense that we increase our probability, and it does make sense that the probability is 1/6. So we didn't even need the formula in this case, but it's good to get used to it because there's some problems where the formula is more necessary.